Hey guys, welcome to my video on 1-2, the properties of the real numbers. The aim for today is to discuss the different subsets of the real numbers and the properties of the real numbers. So to start us off, let's talk about numbers that we've seen before. The question asks, which one of these four numbers does not belong? Explain. Well, the great part about this question is that there is no wrong answer. Each one of these numbers is unique in its own way. For instance, number 1, what do we know about this? It's the square root of 36. Well, hopefully we recognize that 36 is a perfect square. So when we simplify this radical, it simplifies to 6. This we know is called a whole number. Okay? It is the only one of the four numbers that is a whole number, meaning it doesn't have a decimal. It's a nice clean value. So that makes number 1 different. 2/3, what do we know about 2/3? Well, when we simplify it into a decimal, right, it's 6 repeating. We have a pattern that goes on forever and ever and ever, right? 0.6666666. So what's different about this number is that it is a repeating decimal. Okay, 1/5, what's different about that number? Well, when we simplify this to a decimal, we get 0.2. Okay, so now 0.2, this is the only number here in this list that has a decimal, but that stops. Now, we call a decimal that stops a terminating decimal. Okay, a terminating decimal is one that ends, right? Terminating means to end. Now, last but not least, we have radical 21. So what do we know about radical 21? Well, 21 is not a perfect square. Okay, so that's going to cause us a problem under the square root symbol. So when I type this into my calculator, I see that it's 4.582575695 ... Okay, well, we know for a fact it's not a whole number, and we know that this decimal is not going to end. Okay, any radical that is not a perfect square will create a decimal that is non-terminating, right? Is it repeating? Well, I don't see a pattern there. All right, now I'll break the news to you. Even if we kept getting more and more digits, like if we type this into the computer, we would see that there is no pattern. Okay, there's no repeating decimal. So what we call this type of number is an irrational number. Okay, an irrational number is, in decimal form, is just that, a non-terminating, non-repeating decimal. Okay, but there's also something else that makes an irrational number special, and that's the fact that it cannot be turned into a fraction. Okay, radical 21 is the only number here that cannot be turned to a fraction, because we know 6/1 is the same as 6. Okay, so that leads us to our definitions. Rational versus irrational. What are the vocabulary words we need to know for this? Well, rational numbers are numbers that can be written as a fraction. And by fraction, we mean a ratio of 2 integers. So what's included in these rational numbers? Well, we saw 1/5 work, terminating decimals. We saw radical 36, which was equal to 6 whole numbers work. And we also saw that 2/3 worked, right? All of those could be turned into a fraction. Whereas numbers like radical 21, for instance, are all the numbers that cannot be written as a fraction, that are not rational. Now, famous irrational numbers that we should be aware of are things like pi, and hopefully we'll talk about the constant e later on in the year. Okay, and like I said, any radical whose number underneath is not a perfect square will give you an irrational number. Okay, now in terms of decimals, we have rational numbers are terminating, meaning ending, or repeating decimals. Okay, whereas irrational numbers are non-terminating, meaning they don't stop. Non-repeating means there's no pattern decimals. So we have a little cartoon here. It says the 8 is saying to the pi and the radical 2, don't you guys think you should stop fighting? You're both being irrational. That's funny, because pi and radical 2 are irrational numbers, whereas 8, which we know can be written over 1, is a rational number. Okay, so rational and irrational are the two main, what we would call, subsets of the real number system. Okay, a subset is a set whose members are contained entirely within another set. Okay, so of this big group called the real numbers, we have rational and irrational. So you'll see we have two main categories, one with many other little boxes inside and one without. So now thinking about this, is the rational numbers or the irrational numbers going to be the category that has other groups inside of it? Well, like we said before, remember, 6 was a whole number, but 6 can also be rewritten as a fraction. So it's actually going to be that the rational numbers are going to be the one with all the subsets inside of it, whereas irrational numbers are kind of like an island, right? They have nothing else inside of it. It's its own grouping. Okay, so now we need to group the rest of them. The groups that we need to consider are the natural numbers, the whole numbers, and the integers, right? Each one of those are going to be a box. Well, hopefully we can remember what the natural numbers are. All right, natural numbers are what we call counting numbers. They are numbers that you can physically count. So look at your hand, right? You can physically count 1 finger, 2 fingers, 3 fingers. Or think about oranges. You can count 1 orange, 2 oranges, 3 oranges. But you cannot physically count 0 oranges, right? Because that just means nothing's there. So natural numbers are going to be those numbers like 1, 2, 3. Keep going, okay? Whole numbers, on the other hand, are going to include all of our natural numbers, but also the number 0. 0 is considered a whole number. So we have 0, 1, 2, 3. So you can already start seeing the grouping. The most innermost circles called are natural. Okay, and that's the numbers 1, 2, 3, etc. And our whole numbers are right outside of that. And now, technically, because this inner box, right, is inside of our whole numbers, that means that 1, 2, and 3 is also inside the whole number. So I don't have to rewrite them. But the only number that falls outside of the natural numbers is that number 0. Okay? So that's how we want to think of this. So that leaves us with our last grouping, the integers. Now, what are the integers? Well, integers include the natural numbers. It includes the whole number, so that's all the numbers from 0 to infinity. But it also includes our negative numbers. So this includes things like -1, -2, -3, right, etc., all the way down. So it's all of those positive and negative whole numbers. Okay, so we have integers. That leaves everything else to be in this bigger group rational. So those are fractions, like we saw, 1/5 and 2/3. That's our decimals, like 0.2 and 0.6 repeating. That's also includes the negatives of these, right? -1/5, -2/3, -0.2, and -0.6 repeating. All right, so that's how we have to think of these categories. Whereas irrational are going to be all of those numbers that are not perfect squares under a radical, and some fancy numbers like pi and e. Now, all of these are numbers that we call real numbers. Now, in order to do that, we need to define that. So a real number is a number that can be drawn on a number line. Every single one of those numbers we saw has a place on the number line. It might be an approximate place if we don't know all the decimals, but we can draw it on the number line. For instance, pi. Right? Pi, we know, is 3.14. That's an irrational number, but it has an approximate value that I can graph on a number line. So that circle right there, that's closer to the 3, but in between 3 and 4 can represent pi. Whereas negative pi, right, negative value and negative irrational, would be on the other side. Okay? So that's how we want to think of the real numbers. Later on in the year, we will talk about numbers that are not real. Okay, and we will talk about those in depth. So now it's important to be able to compare numbers, to understand them. So the first thing I want to ask is, looking at the two numbers, 5 and radical 22, can we identify the groups that they belong to? So 5, well, we know it's rational, right, because it can be rewritten as a fraction, 5 over 1. We know it's an integer, because it is a positive whole number. We know that it is a whole number because it doesn't have a decimal. And we know that it's a natural number because we can physically count 5, right? So that number 5 fills in all of these categories. Whereas radical 22, since 22 is not a perfect square, is just what we call an irrational number. Okay, now which one's bigger? How do we figure it out? Well, of course, you could type it into your calculator and check that radical 21 is what it's approximately equal to. But if you didn't have a calculator, or if we're talking about SAT time, right, when there's a no calculator section, we need to be able to reason this. So we have radical 22. What we're going to do is we're going to identify the two perfect square radicals that surround this number so we can see in between which two numbers this falls, right? So we know radical 22 is in between radical 25 and radical 16. Why is that important? Well, that means radical 22 is in between 4 and 5. So it's going to be 4 with a decimal. That means that it is going to be less than 5. So if we were to write this, radical 22 is less than the number 5. Okay? And the same thing works for radical 26. Radical 26 versus 6.25. In between what two numbers is radical 26? Well, it's in between radical 25 and radical 36, meaning it is in between 5 and 6. This means that 6.25 has to be bigger than 6. So radical 26 is less than 6.25. All right. So that's how we work with real numbers. That's how we order these real numbers and compare the real numbers. Things we need to remember about the real numbers also are properties, okay? Now, hopefully you've seen these before, but there's some properties that all real numbers satisfy. The first of these properties is the closure property. And the closure property just means that all the calculations basically that you're doing with the real numbers will give you a result that is a real number. For instance, if I add 1 plus 2, we know that's equal to 3. 1's a real number, 2's a real number, 3's a real number. Same thing with multiplication. 1 times 2 equals 2. 1's a real number, 2's a real number, and the answer 2 is a real number. So that's what closure means. Commutative property, the word I want you to think of is order. Okay? The order does not matter in addition or multiplication. Meaning if I add A plus B, you're going to get the same answer as B plus A. So if you ever see the order of the numbers themselves switch, you know you have the commutative property. Associative property talks about grouping. Okay, the grouping changes. You'll see the parentheses move because parentheses tells you what you're going to calculate first. So with the associative property, if you see the numbers stay in the same place, but the parentheses change location, okay, for instance, instead of being around A and B, it's around B and C, you know you have the associative property, okay? Identity, I want you to think of self, like which values will bring us back to the self. In addition, that value is 0 because anything plus 0 gives me that original value back. Whereas with multiplication, 1 is the multiplicative identity, meaning anything times 1 will give us the same value back. All right, so how do you know you have the identity? Well, if you are adding by 0 or multiplying by 1, you have the identity property. Inverses. We've been working with inverses since we started algebra, right? Inverses basically tell me what two things will cancel each other out. So A plus a negative A will cancel each other out because addition and subtraction cancel each other out. Positives and negatives of the same value cancel each other out. How do you know you have the inverse property? Well, the answer brings us to 0. And the same thing with multiplication. A times 1 over A, or the reciprocal, right, will cancel out to give us that identity value of 1. Okay, you know you have an inverse if the answer ends up being equal to the identity value. And last but not least, the distributive, which means when we have a multiplication outside of an addition, we can distribute that multiplication to all the terms inside. Okay, whether it's addition, subtraction inside the parentheses, we can distribute it. Okay. So now, last but not least, let's talk about some vocabulary words. These are words that we need to be familiar with. These are words we need to use to describe our answers. We want to make sure we sound mathematically intelligent, right? Okay, so the first word here is variable. What is a variable? Well, we hopefully know that a variable is a letter that stands for something else. Okay, so looking at our choices here, we see that a variable can be defined as a symbol, which is usually a letter that represents one or more numbers. Okay, constant. Constant, if we think of the word itself, means to stay the same. So where is constant? Well, looking at number 4. Oh, I switched the order here. This should be a 2 and this should be a 3. Number 4, a quantity whose value does not change. Okay, that makes sense. Numerical expression. So a numerical expression versus algebraic expression. How do you know the difference? Well, an algebraic expression has variables. Numerical expression has numbers only. So looking at our last two choices, we either have a mathematical phrase that contains numbers and operations, okay, or a mathematical phrase that contains one or more variables. Variables goes with algebraic expression, whereas numbers and operations go with numerical expressions. Now, of course, we can have numbers and operations in algebraic expressions as well, but you really need that variable to make it algebraic. And the last set of vocabulary words: terms, coefficients, like terms, and constant term. So in order to know what a like term and a constant term is, we need to pay attention to what a term is. And basically, a term is just one of those individual values that you are adding or subtracting to each other. Okay? For instance, 10x to the third power is a term. Okay, minus 14x squared is a term. 3x is a term. Each one of those is individually a term. So that means that a term is an expression that is a number, a variable, or the product of a number and a variable makes up our terms. Okay, well, what is a coefficient? The coefficient is the numerical factor of a term. So on a single term, the number that we are multiplying by is going to be our coefficient. So in this, if we're still looking at 10x to the third as a term, 10 is our coefficient. If we look at negative 14x squared, negative 14 is our coefficient. 3 is our coefficient here. Negative 4 is our coefficient here, etc. Okay, so that's our coefficients. And like terms are basically terms that have the same variable raised to the same power. So if we see the same exponents, okay, they're considered like terms, and we can actually combine these like terms. So let's take a look at this example down here. Okay, do we have like terms? Well, we do have a couple of pairs. We have our x cubed terms. Right here, 10x cubed minus 4x cubed. We combine those by adding their coefficients. So a 10 plus a negative 4, or 10 minus 4. That gives me a 6x to the third. There are no x to the second power like terms, so we bring that down. But there are x terms that are like 3x and 4x. We combine those by adding their coefficients to give me a 7x. And last but not least, right, we have what is called our constant term, okay, which is a term with no variable. The constant term goes at the end because typically we represent this in what's called standard form. Okay, standard form just means that we list the exponents in order from greatest to least, right? 3, 2, 1, none. Okay, so that's pretty much sums up everything we need to know from 1-2 and 1-3. And I ask that you attempt these practice problems in your notebook and check your answers to the answer key online.